Osmosis. So Mia, what's going on with that little kid's finger? When does that happen? Stay in the shower too long. Yeah. So Megan, is water going into or out of that kid's finger? Huh? Into? Do you agree, Cameron? Water's going into that kid's finger? Does everybody agree? Why? She's right. Kid gained weight taking a shower or swimming too long. Sucked up water. What's that? Swelled up because it sucked up water. It's the old word, osmosis. Nature wants things to flow from what concentration to what concentration, Kenneth? What's natural? To flow from a region of what concentration to a region of what concentration? Greater to lesser, right? Things mix. You can't stop it. That's just nature. So you have the little kids swimming in the swimming pool. You'd think that the water would be dirty and stuff, right? That, oh man, it's dirtier inside the kid? Well, concentration-wise, yes. Pure water, concentration is always the amount of stuff over some volume unit. Water is 55.4 moles per liter, pure water. So inside this swimming pool, it's definitely not 55.4 molar because there's a lot of other stuff in there. But it's much more concentrated than it is, water's much more concentrated in that swimming pool or that bathtub or that shower in comparison to inside your body. Look at inside your body. You've got, yeah, we're majority water, 90-some percent, but that's not even close to what the 99% or higher in a swimming pool. So water's going to flow from that swimming pool into your body. You can't stop it because your water's less concentrated inside you. Okay. Here's a little video. See if this works. Have some wilted lettuce. Speed it up 720 times. What'd they put the lettuce in? Water. Right? So I don't need to throw that stuff away. Just wait 3 hours and some water. We've got, we need applications of this though. And an application of this really kind of depends on an inkling of an understanding of this chart. So we've got size up on top and microns and nanometers and things. And we've got things listed like blood, glucose, and viruses and salts. Where would you say, Bowdy, a water molecule fits in that list of size? Where would a water, it's not in there. Where would you guess? You almost need to, I don't know, where you get the feeling for the size of things, but a water molecule is, it's just H2O, right? The other things on this list, viruses and cells and vitamins and insulin and salts, there's a lot more than just 3 atoms. Water is extremely small. Water is only about 0.2 nanometers, so it's way over here. Water is 0.2 nanometers. So it's smaller than anything that's on this table. Okay, let's take a look at an animation here. So what's the application of this? Well, let's say water's the green. So I'm going to shoot a bunch of green molecules on this side. Okay, and there's nothing on this side. Now what's separating them is this wall. But let's make the wall semi-permeable. Audrey, semi-permeable means what? Right? Let's throw in some, I don't know, some of that virus stuff. Semi-permeable means only some stuff can go through. And the simplest one is the size. So let's put some little holes, semi-permeable membrane, that only water molecules can fit through. So you are witnessing the O word. You're witnessing what again? Osmosis. So water is going from a region of, let's make it more concentrated here. Water is going from a region of high concentration to a region of low concentration. Okay? You just have to wait. Now notice it's going both ways. But it's kind of easier to tell if the guy keeps track of the concentrations. Right? And we can make this region a lot higher. And sooner or later, they'll end up evening out in concentration-wise. Okay? Now, think about this, though. You're in the desert. You're one of those Arab guys, and you've got money to burn, but you don't have any water. But you live right there next to the ocean. Can't drink it, though. What if, here's your, let's start all over. Imagine this. Okay, you've got all this seawater, right? Let's not have these guys yet. You have all this seawater. Okay, but you want there to, you want pure water, right? So pure water would look like this. I need a lot of stuff, a lot of water molecules in there, all right, to make it much more concentrated. Okay, you want pure water. I can't get any more in there. Anyway, but it's higher in concentration. So you want pure water. You want one to go to the other one, right? You want to get that salt water converted to pure water. Is that osmosis? That's the opposite of what it's supposed to happen. So they call that not osmosis. They call it what osmosis? Reverse osmosis. So, because if you put these little membranes in here, right, you're going to get osmosis to occur, and that's just the opposite of what you want. Your pure stuff is going to go away. So what we need to do is to apply pressure on this side. And pressure is just pushing this. Notice how you have molecules moving through. Their tendency to move through is more than the tendency to go down the other way, right? Concentration high to low. So if you can stop that tendency of going from high to low, you'll stop it by applying a pressure on this side. It might be easier to illustrate. Well, there'll be another animation up here. It might be easier to illustrate. But this is kind of disgusting. I like to have these little videos and things. This is almost too disgusting, so I just stopped the video and took a picture of it. What did they do to that little snail? They poured salt on it. Yeah. And then he had all these little bubbles on the little snail. Why? What was going on? He's dying. Yeah, most definitely he's dying. But what? Why? All right? It's sucking out all the water. You dumped enough salt on there so that the concentration of water outside the snail is lower than the concentration of water inside the snail. Same thing would happen to you. Okay, if you had the skin of a snail, all right, that's really slimy and permeable to water like that. So that's why humans don't have that type of slime on your skin, I guess. Here's an animation of osmotic pressure.
When two solutions with the same solvent are separated by a semi-permeable membrane, solvent molecules migrate through the membrane from the solution of low concentration to the solution of high concentration. A concentrated glucose solution is added to an inverted funnel with a semi-permeable membrane, and the funnel is placed in a beaker of pure water. Water flows from the beaker into the funnel. The upward flow of solvent stops when the pressure of the solution above the membrane equals the osmotic pressure, pi.
It's kind of confused. They kind of flipped the language I was using. But can I pause? It wouldn't let me pause. So the point is, all right, we have this beaker of pure water, and then you've got something that's not pure water in here, and then you've got your semi-permeable membrane. So that means only what can go through this? Water molecules, because of its shape, size, right? Because the holes are so small. So when I've got something that's not pure water and something that is pure water, the water is going to flow from where to where? Into the thing, because it always goes from what concentration to what concentration? High to low. So this is, you can't get it any more concentrated because this is pure. So it's going to go into where it's dirty, right? Things just get dirtier. You can't stop it. So, and if it's flowing in there, the level here is going to keep going up until the rates of water molecules going in and out of through that membrane on both sides reach the same. And what the curious thing is you can stop this if you apply pressure on this side. Well, what does pressure do? Well, if you apply pressure on how can you apply pressure? Blow on it, right? Have a pump, whatever, add some weight, whatever, just something that's going to push down on that surface. And by adding pressure, now water molecule, you're going to increase the rate going the other way because you're adding pressure. You're pushing that stuff through there physically, forcing it through. So you don't want to apply any more pressure than just to stop the rate of it going up, right? So pure water, dirty water, it's going to go up. But you can stop it by applying just the right amount of pressure. Apply too much, and you'll be doing what osmosis? Reverse osmosis. You don't want to apply that much, just enough to stop the flow from going up. That's osmotic pressure. So, and it's useful. Why is it useful? Because look at these equations. If you can figure out what the osmotic pressure is of something, okay, that's what the pi is, okay, we can actually get molecular weight. And that's what the homework's going to be. So and that's really why they had this chart, because it's so applicable. You can use osmotic pressure to find the molecular weight of a lot of big, ugly things, right? Cells, yeast, whatever. Okay, it's very useful. Okay, you can also, so that's osmotic pressure is our pi symbol. Oh, they want us to throw units in, or I want you to throw units in. What are some units of pressure? But you know what? Let's do the hint, though. Start with R. Okay. Kendall, you remember, what was big R? What was it called? What was it called? The gas?
I don't know, I know the number.
What's the number?
It's
0.0821.
821.
Okay. Enrique, you remember what it was called? This big R? Something constant. The gas constant. It was in our PV equals nRT equation. Remember that? It's the exact same R that we've been using before, and that's why Kendall knows the number. But what's more useful than knowing the number are the units, because the units are going to tell you what everything else needs to be in this equation. Connor, remember what the units were?
Atmosphere times grams.
Does anyone remember? I give you this stuff, but I just wonder if you remember. Liter atmospheres over moles Kelvin. Okay. So that's what our big R is. And there's different R's. You can also use 8.314 joules per Kelvin mole, but that's not going to be as useful as this one because the pressure units and everything are obvious in here. So pi is the osmotic pressure. So if you're going to use this equation, Anessa, pi had better be in, your osmotic pressure better be in what units? ATM. You have no choice. What were some other units of pressure, though? Then odds are Andromeda, the homework is going to give you the osmotic pressure, not in atmospheres, but what do we call it, of mercury? Millimeters of mercury. Do you want to remember? How many millimeters of mercury were in one atmosphere? 760. And I gave you that stuff too, but just, right? Odds are you're going to have to do some converting on. I know that's pretty much coming. Okay. T must be what, Jose? Temperature. In units of? Kelvin. Jose, how do you get something in Kelvin? They're not going to give it to you in Kelvin. They're going to give it to you in what units? Celsius. How do you get Celsius into Kelvin? Cameron, how do you get Celsius into Kelvin again? Yeah, you add 273 to it. Technically 273.15, but you get good enough answers with 273. Okay, so we've got the R, the T, the pi. The thing we're missing is big M, Megan. What's big M? It's both, right, to take care of them. It's moles over liters. Well, we kind of know that as what, Kenneth? What do we call moles over liters? No. Starts with a C. Or is that, or an M? Molarity, which is a unit of concentration, right? So that's our concentration, but it has to be in units of moles per liter. It's big M, molarity. Okay. So how are we going to get molar mass out of this? I'll just give you a heads up, because I think that's one of the first homework questions we're going to do, but they're going to ask for what's the molar mass of this stuff. I think we already had last class we did something like this. We started out, Bowdy, with molar mass as units of what over what? Grams per mole. And then the homework is always going to tell you the number of the grams of the stuff. They're going to give that to you. Because there's no way you can calculate that. I mean, you have this osmotic pressure, this little doohickey here, and you put so much substance in there. They got to tell you how many grams they put in there. And then they'll measure the osmotic pressure and things. They'll just ask for what's the molar mass. So you got to figure out moles from this thing. Right? That's what you have to find. That's what you have to find, using all these equations down here. Okay. So notice how you see how it's going to be two steps. First, you have to solve for big M, and then you solve for moles using the big M equation. And then you substitute it into our molar mass, and you'll have your molar mass. So we'll do one of those. But look at the equations, man. They're getting longer. We've got, these look familiar. Right? I think we have these. This stuff should all look familiar. We've done that before. But now they've just added these. Well, and our osmotic pressure. But they've added these little I's. Kendall, what's a little I? It has something to do with ionic. And you have to have solutes that are ionic to be using the little I. Otherwise, see how the equations are exactly the same, but no little I, if it's not an ionic compound. Man, we should see if you remember that. Mia, how do you remember if something's on look at a compound. Is it ionic or is it molecular? How do you tell? If there's a metal. If you see a metal, that's right. That's okay, Steph. If you see a metal, it's got to be what type of compound? Ionic. If you see a metal, it's got to be ionic. Okay? So that's half the story. If you see a metal, you know you're going to have to be using the equations on the right. But that still doesn't tell you what little I is. So I added this morning. We've got some compounds here. Steph, little I is the number of ions. So our solute is potassium sulfate. This breaks up into how many ions? 6? 2 or 3? I don't know. All right. Let's put in the charges. That might help you. K has a what charge? +1. And there's a hint. you can put parentheses around these polyatomics. There's a 1 down there. Sulfate has a -2, because there's the 2 right there. So this is going to break up into how many K plus ions? 2 of them. How many sulfate anions? 1. So the total number of ions would be 3. So you're going to have 2 potassiums and a sulfate. So that means I is going to be 3. So these ions, look at, they just really enhance the change. Whether you're talking about osmotic pressure or the change in vapor pressure lowering, boiling point elevation, freezing point depression, they really magnify it. Okay? So you got to be careful when you have these ionic solutions. Enrique, what's I if your solute is potassium bromide? It's definitely ionic because you got a K again. So little I would be, why?
Because
Connor's too nice to you. You got a K plus and a Br minus. So 2 ions. How about C? Anybody? How many ions? 4? D. It's not ionic, so you better not be using the I equations, right? Don't use, I is not applied. It's, all right? What would you say? Don't use I. Don't use I. All right, because it's a covalent compound, carbon dioxide. You don't see a metal. Colloids. The book just threw this in here. I don't know why, but they did. Okay. Colloids is in the Tyndall effect. So if I have pure water, I can shine a laser through it. You can kind of see it. Can you a little bit maybe? See the light going through there? If I have salt, you can kind of see the light going through the salt. Okay? And the Tyndall effect is just take a big molecule and it really scatters the light so you can see the laser light going through the solution, and then they do some fancy figuring out what the intensity is and the angles, and they can figure out the size of these huge molecules. It's called the Tyndall effect. So I'm going to take some big, fat, huge fat molecules. Coffee mate. It's just essentially I'm adding milk. Right, so I'm adding some fat molecules. Whoa, I added too much. This is going to be really, I added way too much. But it'll get the point across. All right, you can easily see it. That's the Tyndall effect. That these molecules are, these blobs of stuff are so big, they don't call them molecules. They're just tremendously big globs of stuff in solution. And so they call them colloids. They're just big. But still solutions, it's still evenly distributed. So it's kind of odd. Alrighty then. Here's our first question. An aqueous solution contains 0.296 grams of a polymeric molecular unknown compound. If there's 125 mils of solution, temperature is 25 degrees Celsius, osmotic pressure of 2.58 millimeters of mercury, what's the molecular weight of the unknown? Anessa, you're so lucky to tell us how to do this.
So you change the 2.58 millimeters of Hg, you add 760.
Wait.
To make
We're not going to add 760.
times 760.
Well, maybe just do this. We'll convert it to units of ATM. We'll need that in the units of ATM. But before we do all the little individual steps, what's the big picture you're going to do to solve this? And the final answer, what are you going to do to get your final answer?
Final answer is going to be in grams per mole.
Final answer is going to be in grams per mole.
So you're looking for big M.
Whoa. Oh, yeah. Okay. Final answer is in grams per mole. We're going to need big M in the, we don't have big M written up there yet. Andromeda, I just like to start at the end because there's less ambiguity, I think. Because they're asking this, That's why I'm going to start here. They're after molecular weight. How are you going to get the grams? We don't know molar mass. That's what we're trying to find. Does anybody see it? Where'd that stapler go? How do you get the grams? Yeah.
Are we getting, like, at the end of this, is this all supposed to be for pi, MRT?
Yeah, we can open up to that question. Which equation are we supposed to be using in this mess? Look at all these. Which ones are you going to use? MRT definitely, because it's, well, we're going to be using a pi one definitely because it mentioned the words what pressure? Osmotic pressure. So which one of these are we going to use? We're kind of skipping ahead, but that's okay. The one without the I. Why?
It's molecular.
Yeah. So there's a couple hints. One is they said molecular. The other one is well, if it's going to be the one with the little I, they got to tell you what the ionic compound is. They don't even say what, there's no letters or anything up here. So molecular is one hint. The other hint is polymer. All that is, I don't know if you remember writing the formula for sugar or something. You had all these C's, H's, and O's. Well, just keep going on and on and on. Hundreds and hundreds of lengths long. And that's your polymer. It's a huge molecule. Okay, so we're definitely using this equation. But it doesn't, we want to get here. How are you going to find your grams or your moles? Jose, you got an idea? How are you going to find the grams or the moles? An aqueous solution. So what they did is they took 0.296 grams of this polymeric substance, right? And they put it in here, okay? Put it in 125 mils of water, immersed it in pure water, and they stopped the liquid from going up by applying 2.58 millimeters of mercury. So you already have atmospheric pressure on here, but they applied 2.58 millimeters of mercury in addition to what's atmospheric pressure. So, you're trying to find the molar mass of this stuff. And the molar mass is grams per mole. It gives you grams. How many grams? 0.296. You're halfway there. You're halfway there. Okay? They told you that. So we only got to figure out moles. Cameron, how are you going to get moles? Anybody give him a guide? Help him out? Use the big M equation. So there's two ways you can go about this. You can substitute in the big M equation here if you're really comfortable with algebra. You can put in your moles over liters here. But I think what we've been doing in class is if we solve for big M, and then we use the big M equation. I think that's what we've been doing in class. So if we're going to solve for big M, we better know everything else. Megan, what are you going to substitute in that equation so you can find big M? Pi's got to be in the atmospheres. Okay. So a guide on, I think, working out these problems is notice how we started out our discussion here. You see little tidbits. You know that, oh, I'm going to convert millimeters of mercury to atmosphere. That's just going to slow you down. You want to start with the solution. Otherwise, you could just be randomly doing things and really not have a plan, a guide. So if you start with the answer, life is much healthier. It'll go smoother and much less frustration-wise. Now you've got a reason to convert it, okay? Because you may not have needed to before. Okay, so I got to convert millimeters of mercury into atmospheres. And the number goes where, Kenneth? Yeah, and it was 760, right? Okay, so now you know what the 8 atmospheres is. You know what R is. Go back in the notes and find it. Someone told us how to get T. See if you can get an answer for this. That's osmotic pressure. Pi is our osmotic pressure symbol. Yeah, pi is our osmotic pressure symbol. That's the ATMs. Yep. Yeah, so go over here.
I need to change that.
Yeah, change that. That's ATMs. That pi is ATMs. Yeah, if you missed that. Yeah, see that pi is ATMs. So you should do all this in one big step to get your big M. And then set up your M equation and solve for moles. Mia, what did you get for big M? 1.3 times 10 to the negative 4. You can write moles per liter or big M. Did anybody else get this number? Okay, good deal. Then set up your big M expression. Oh. And right. So this number, let's put it in right there and get your answer.
Oh, is that a -5?
Yeah, I got, for my moles, I got 1.625 times 10 to the negative 5.
Okay, because that's what I did. Like, the reason why I did was because I did 1.39. That's the thing.
It should be close. Whatever. Okay. So for this one, I would take this number, 3.39, and then times 10 negative 3 is EXP. All right? Divide it by this, divide it by 298, and you'll get that. Did anybody else get a huge answer?
Yes.
And it should, because it's a polymer. It's this huge, huge compound. Very huge molecule. I got about, what, 18,200? Depends on how many sig figs you used, but somewhere around 18,000 grams per mole. Somewhere around there, right? Depends on your rounding and how many digits you carried. And the more digits you carry, the easier it will be to match the answers in the back of the book. Okay. You okay with that? Enrique, make sense? Okay, setup number 2. See if you can get number 2. We've got about 5 minutes. A mountainous location, the boiling point of pure water is 95 degrees Celsius. Makes sense because they're higher. There's less atmospheric pressure. As you heat up the liquid, the vapor pressure reaches atmospheric pressure a lot sooner, so it boils sooner. How many grams of sodium chloride must be added to a kilogram of water to bring the boiling point back to 100? So they want to boil it like the dudes at sea level. But they have to add a solute. They're going to add salt, sodium chloride.
The delta TB equals I.
Yes. I don't know if you heard Anessa, but she picked which equation? She was right. Ionic side, delta TB. Exactly. This is the one you have to work with. You have to work with that one. Okay. Oh, shoot. We're missing something on this kind of question, aren't we? It needs to be given what Kb is for water. Is that written somewhere? Kf for water. Oh, I just tell what's the number? Oh, you don't have to look it up. I might have it in here. It's 0.512? Yeah. It's 0.512. Thank you. Degrees Celsius per little m. So we need that. Okay. Oh, I have to give you all those constants. Yeah. Okay. You're after grams of sodium chloride. Does anyone see the big picture? How are you going to get it? Get it from CM. Set up the CM equation. So you're going to have to do this first. First, find CM. Second, CM will be moles of sodium chloride all over, what was it? Kilograms of solvent. All right? So here's your grams of sodium chloride. You just have to solve for moles and convert it. So this is going to be a 3-step problem. Here's the first step, find CM. Second step, use CM to get moles. Third step, convert moles to grams. All right. So there's your big picture. See if you can get it. What are you going to plug in for delta TB? 5. You ain't going to see that. 5 has to equal, my Kb is 0.512. What are you going to plug in for I? 2. So solve for Cm. Set up the Cm equation, get moles, then convert moles to grams. Okay, so these problems are getting longer.
They're easier than yesterday.
Really?
Yeah, I got confused in the whole. How do you get to AMU? Yeah, they had all this AMU stuff in there. I was trying to figure out how to do that.
AMU is just grams per mole.
Yeah.
They're not talking about the mass of a single molecule, right? They're just talking about.
They were
They
like,
wanted to see that like the molecular formula.
Well, you have to show me the question. I'll help you out. See what the heck they were talking about. Okay, so come by and I'll be glad to work with you on this stuff. But you have the big picture.